All right, we are going to go ahead and start lesson 3. We are still in section 7.1 today, and we are going to look at kind of what happens when we can't use vertical representative rectangles to describe the area of the region or the entire region between two curves. But before we get started with that, I want to make sure that everyone is clear on if we are not given a nice pretty graph, we need to, when we do these problems, be able to find the intersection points of the functions that are given to us. So if you notice, these functions are written in terms of y. So I want you to go ahead and pause me and find the intersection point between x equals 3 minus y squared and x equals y plus 1. Okay, so doing this problem, we're going to go ahead and use our equal values method and set these two things equal. And then from here, we are going to move everything to one side. So I'm going to get my y squared to be positive. So I want it to be 0 equals y squared plus y and then minus 2. All right, at this point, we can go ahead and see that this is going to factor nicely. So we have y plus 2, and then we have y minus 1 equals 0. So these equations, I'm not going to call them functions, you'll see why in a second, are going to go ahead and intersect at y equals 1 and y equals negative 2. Now, you might be saying, okay, go ahead and find the x value of those intersection points, but I'm going to leave it at this, and you'll see why here in a second. So if we scroll down to example number 5, it says find the area of the region bound by the graphs x equals 3 minus y squared and x equals y plus 1. Okay, now those are the two functions or equations that we just worked with in the warm-up, and I did that on purpose. Okay, now if you look at the graph of this, which I copied it twice, okay, you can see right off the bat that this first equation, we can go ahead and write, this is not a function. Okay, it fails the vertical line test. So this is kind of the first hint of when to identify what I'm going to teach today. Okay, because most of the time when you find area between two curves, you're going to do exactly what we did in lesson number 1. You have your upper and your lower function. But if we go down to the second picture first, and we try to use what I taught you 2 days ago, okay, you can see here in this picture that the person tried to use vertical representative rectangles. Okay, and in this area here, it's okay. Okay, because you can see that y equals x minus 1 is your upper, and then you can see that x equals 3 minus y squared is the lower. But the problem occurs, okay, when you get to this related rectangle right here. What do we notice? We notice that the same function is the upper and the lower portion of that representative rectangle. Okay, so we can see, if we go ahead and write it out, that right here, the same function which is x equals 3 minus y squared, is both the upper and the lower part, we'll just say, of the rectangle. Okay, and when this occurs, we have kind of two options, and I'm going to teach you the main option, which is to turn to, so what are we going to use? We are going to use horizontal rectangles. Okay, and that is what I'm going to show you in the diagram above here. Okay, so with horizontal rectangles, again, the hint is when one of the two equations given is not a function, it's probably going to at some point fail that, it is going to fail that vertical line test, which vertical rectangles represent vertical line. Okay, so we are going to turn to a horizontal rectangle. In a horizontal rectangle, we are going to look at it from the perspective of the right function versus the left function. Okay, and we are going to integrate with respect to y. Okay, so the big key here is you have to solve the equations for x. And at the bottom of your note sheet, you can see that we're going to go through key points here in a second. So what we're going to do is we are going to set up our integral, and we still want to pay close attention to these points of intersection, okay? But when we integrate with respect to y, we are not looking at the x values where they intersect. We are looking at the y values where they intersect, which we did in the warm-up. Okay, so we can see that if we look on our y-axis number line here, we are going to look at -2 to 1 being our limits of integration. Again, looking at those y values. So now we are thinking about, okay, the upper part of the shaded region is not, we're not looking at up and down, sorry, we're looking at right versus left. Okay, so we are going to take our rightmost function, which is 3 minus y squared, and we are going to subtract our leftmost function, which is y plus 1. dy. Okay, so when you see dy, that gives you a big hint that they're probably integrating with horizontal rectangles. So if we clean this up a little bit, and we have -2 to 1, we are going to look at -y squared minus y, and then plus 2 dy. And then like we talked about on Monday, you can go ahead and plug this into your calculator. Now just use x's instead of y's for your calculator. Go to calculate option 7, enter -2 and 1, kind of ignore the picture ultimately, and we are going to get 4.5. Sorry, my phone is buzzing away right now. Okay, so the moral of the story is using horizontal rectangles, we found the area of the shaded region, which is 4.5 units squared. Okay, now we are going to go over the key ideas of kind of what sets vertical and horizontal rectangles apart here at the bottom of your sheet. So I'm just going to highlight some key ideas as I work through them with you. So the key idea is when finding the area between two curves, you need to first decide whether your integral should be written in terms of x. Written in terms of x means equations are in y equals form. That is what you are most used to. Versus if your equation should be written in terms of y, which are x equals forms. And sometimes, usually, that indicates that those are not functions. So if we look at when we are in y equals form, okay, you need to make sure that there is a clear upper and lower function for the entire region, not just for a portion. Be careful, it's sometimes easy to trick yourself. When that is the case, you are going to use vertical rectangles, meaning you are integrating with x's, with respect to x. So everything in your integral relates to x. You look at the x-axis for your limits of integration, and then your equations are written in y equals form because that will put x's in the integral. Okay, now on the opposite end of the spectrum, okay, if the top function is also the bottom function at some point, it doesn't have to be the entire interval, try integrating with respect to x. Okay, now I'm going to look at kind of what that means with these bullet points here. So when you integrate with respect to y, sorry if I said x, when you're integrating with respect to y, that cues using horizontal rectangles. You need both equations in x equals form. And you're not looking at upper and lower, you're now looking at right and left functions. So the integral, the technique for finding the region under the curve, is going to be the integral from a to b, and those are found on the y-axis, not the x-axis, okay? It's where the functions intersect. And you're going to, in most cases that we are going to do, take right function minus left function. And again, what are we integrating with respect to? Y. So it's going to have a dy at the end. Okay. So we are now going to look at two more examples where we are going to use horizontal rectangles, okay, and then I'm going to give you some practice for the next 2 days on that. Okay, so this next problem is asking us to find the area of the region bound by the curves. Right away, when I see x equals 2 minus y squared, I'm thinking, okay, y squared, usually that's a parabola on its side, so we're probably going to use horizontal rectangles. And then we're also going to use y equals negative x. Okay, so let's go ahead and graph these. You can always use your graphing calculator, okay, but this is going to be, might be easier to look at it in terms of y equals. So sometimes you're going to see people go ahead and solve for y anyways. So we have y squared equals 2 minus x. So y equals, this is where you can see the two-part function, plus or minus the square root of 2 minus x. So when you look at it this way, we can see it's going to be flipped over the y-axis, okay, and it's going to be shifted back to, to the left to, but really that's going to end up being to the right to. Okay, so we have this, and then we can make a parabola on its side. Okay, I might erase some of these. So we have our parabola on its side, and then we need to also go ahead and graph our line with negative slope. Okay, so we can go ahead and graph that. Okay, that is bad. I'm not doing as well today on my graphing, sorry. There we go. So we are finding the area of the region between the two curves. Now, if we draw a vertical rectangle, okay, look at this little portion here with my red pen. My vertical rectangle utilized the black function for the upper and the lower. So immediately I found the problem spot. So I'm going to turn to trying to look at horizontal rectangles. And you can see that in every spot we utilize a clear right function and we utilize a clear left function, okay, which is purple. So the first thing before we kind of jump ahead of ourselves, or we can go ahead and start, and you can see kind of what happens, is if we set up our integral, right away we're asking, well, where do these functions intersect? Okay, now you can your graph is probably better than mine, but in the case that we don't have an accurate graph, we need to figure that out. So the first thing you need to be careful of is this function, or equation I should call it, is set equal to x, but this is really set equal to y. So I just quickly need to get the second equation set equal to x, so divide by -1. Now I can go ahead and use my equal values method. 2 minus y squared equals -y, and solve. Okay, so I have y squared minus y minus 2 equals 0. This is looking kind of like what we did on the front. We have x, minus 2 times x plus 1 equals 0. So the intersection points, why did I change to x? See, we're so, our brains are so used to working with x, sorry. It's going to be the same numbers, but I want to keep consistency. So we have y minus 2, and then we have y plus 1 equals 0. So then y equals 2, and y equals -1. Okay, and you can kind of check if you look on your graph, -1 and 2 are definitely where those graphs intersect on the y from the perspective of the y-axis. Okay, so we have -1 and we have 2, and then my right function is, I have to use, let's see, 2 minus y squared. They have to be written in terms of y. And then subtract, okay, we need to use this function here because it has to, again, be solved for x. So minus y dy. So then I clean things up, -1 to 2. So I have -y squared plus y, and then plus 2 dy. Okay, let's go ahead and review our integrating. So we have power rule, -1/3 y cubed plus 1/2 y squared plus 2y. And then we are integrating from -1 to 2. Okay, you could go ahead and plug these numbers in, or at this point you could use a graphing calculator with the integrate feature, and we end up getting, again, that region is 4.5 units squared. Now I promise the answer will not always be 4.5, but the numbers work out nicely there. Okay, so one more example for today. So we are going to look at a problem where you could do the problem either way. And I'm going to actually do the problem both ways so that you can see some cases why we'd want to use one or the other, or sometimes you just have the choice of what you prefer. So we are asked specifically to integrate with respect to y. Okay, so right away I'm thinking horizontal rectangles. Okay, but let's go ahead and get our graphs going. So we have x squared plus 2 is going to be a parabola that is shifted up 2. And then we have y equals 4, okay, which is just going to be our horizontal line at 4. So we are being asked to use horizontal rectangles, so let's draw those in. So if we're using horizontal rectangles, you might say, well, wait, those are using the same function, so that kind of goes against what you've been saying. Well, if we are differentiating with respect or integrating with respect to y, we need to get the functions in terms of x equals. So if I solve for x in this first function, I have x squared equals y minus 2. So what do I end up getting? I end up getting two equations. Y equals plus or minus not y equals. X equals plus or minus the square root of y minus 2. Okay, so the positive square root of y minus 2 is in the first quadrant, and then the negative square root of y minus 2 is in the second quadrant. So I think I can call the first quadrant equation my right function, and I can call the second quadrant equation my left function. Now, what the heck does y equals 4 have to do with anything? Okay, this represents a limit of integration. So now we are looking for this shaded region on the y-axis, kind of what is defining our space, 2 to 4. Okay, so now we're going to go ahead and take our integral from 2 to 4 of the positive square root of y minus 2 minus the negative square root of y minus 2 dy. Okay, now from here we get 2 to 4. The double negative makes a positive, so we have 2 square root of y minus 2 dy, okay, which I can rewrite as 2 times the integral from 2 to 4 of the square root of y minus 2 dy. Okay, now let's do a little bit of blast from the past review. We see a function inside a function, so I can go ahead and look at using u substitution. If I make u y minus 2, then what is du going to be? What's the derivative of y minus 2? It's just 1, so it's dx. Okay, which because I popped this 2 out front, I really have a 1 sitting here, so I'm good to go. So I'm not going to put in my limits of integration on this step. So I have 2 times, instead of the square root, can I go ahead and write u to the 1/2 du? So when I integrate, I get 2 times 1/2 plus 1 is 3/2, so 2/3 u to the 3/2. So I'm really considering 4/3. Now I'm going to input my u, y minus 2 to the 3/2, and I'm integrating. Now I can put those back in from 2 to 4. Okay, now when we plug in and do our integration, I'm going to kind of skip some or do some intermediate steps along the way. We see 4/3, and then if I input my 4, then I can do 4 minus 2 is 2, so I'm looking at 2 to the 3/2, and then minus 4/3, but then what do I get? 2 minus 2 is 0, so that goes away, which is nice. And then I know that 2 to the 3rd is 8, but then over 2 means really take the square root. So the square root of 8, so I have 4/3 times the square root of 8. Well, what is the square root of 8? It's 2 root 2, because the square root of 4 is 2, and I can't take the square root of the other 2. So I have 4 times 2 is 8 root 2, that's just simplifying radicals, over 3 units squared. That is the area of the region, which is not as nice. And if you plug that in to your calculator, if you use the integrate feature, that's approximately 3.77. Okay. Now, if you do this the other way with respect to y, okay, where is it going to get a slight bit messy? It's still very doable, but if we go back to the original problem, okay, the first thing that we have to figure out in the original problem are these intersection points, but we have to look at them from the perspective of the x-axis, okay? And we can see that on the x-axis, they're not necessarily perfectly a whole number. So in that case, you need to go ahead and solve for where they intersect in terms of x. Okay, so if I show the work maybe up here, and I set x squared plus 2 equal to 4, because they're both in y equals, okay, and I move my 2 over, I'm going to go ahead and get, when I square root both sides, x equals plus or minus the square root of 2. Okay, so that might seem a little messy, but those are our limits of integration when we differentiate with respect to x. Okay, so hang with me. So if I scroll down here, okay, and I kind of draw a line here, I can look at integrating from negative root 2 to the square root of 2. Now, what is my upper function? My upper function in this case, when they're in y equals form, is 4, minus what is my lower function? My lower function is x squared plus 2, and not dy. We're now differentiating with respect to x. We're using vertical rectangles. So when you do this and clean it up, go ahead and just use the calculate feature, because the calculate feature still lets you use square roots as your limits of integration. Okay, it is going to give you the approximation of 3.77, okay, which is what we got above. Okay, now you could certainly also integrate by hand, and some of you guys might be saying, I prefer this because it avoids having to use u substitution. Okay, but if you are asked to specifically differentiate with respect to respect to y, you have to follow that. Okay, so that's where you have to know what I just did in purple. Okay, So that is all I have for you today. Please make sure to do the book review problems. I've intentionally chosen the specific problems, utilize the features of kind of the step-by-step solutions that the book puts out. I will always ask you to check those the next day. So if you want to just go ahead and do those alongside of while you work, that can maybe lessen the time that you have to spend to make sure that you're doing things correctly. Again, let me know if you have any questions. Send me emails. I want to be in touch with you. But if this is making sense, keep moving right along. You're doing great. And we'll move on to lesson 4.